Hello folks, this is video number 21 in the playlist which is devoted to the dynamics aspects of motion design application which is buried in the 3D Experience platform. I'm going to be solving an impulse problem on a suspended bar, and the problem that is going to be solved is a bar like that of length L, mass M, and it's hinged at this point here, and there is a torsional spring which resists the motion of the bar, and an impulse is applied, which means a very short duration force to that bottom point, and obviously what's going to happen is immediately this vertical bar is going to tilt to the right, and that's the problem that we want to solve. Now, there are some dimensions here that I'm going to be giving, and you can see that I'm modeling this bar with a thin plate like that, which is okay. And there's a revolute here, there's a fixed hinge, and there's revolute joint between the bar and that hinge. Now, this problem's analytical solution can be found in the book by Rao, and I'm using that to compare my 3D experience result. The uh, specifics of the dimension and everything are given here, and we're going to come back to that in a minute. Notice that if the length, thickness, and the width of the bar is given, and the density is density of steel, for example, you get 7.76 kilogram bar. Okay. Now, we're talking about an impulse. That means a short duration force. So here's the way it's being applied here. I apply a force of 1,000 Newton over a hundredth of a second, 10 millisecond. Now, if you calculate this area, you're going to get 1,000 times 0.01, which is 10 Newton second, and that is uh, the impulse that's applied. Now, in motion design, you're not going to apply an impulse, you're going to input basically this function. The objective is to find the two things. One is the angular velocity of the bar immediately after the impulse is applied. And also okay, the other thing that we want to find is the maximum angle of tilt of the bar. Now, in that reference that I showed you, the angular velocity immediately after impulse is given by that expression, and this is using the impulse momentum equation, and this one is using energy equation. You can find the maximum deflection of the bar, which is going to be based on this data that I've given here. Is going to be 7.72 rad per second for the velocity, and roughly 15.9 or 16 degrees for the deflection tilt. When it comes to running this thing in motion design, I will use a short duration of 0.3 second, because do the simulation of that, because actually what that impulse does is applies an initial velocity, and if you just let it go, this thing will oscillate back and forth like a pendulum. And we're not interested in that. We're interested in to find the velocity immediately after the impulse. Okay, so I'm going to do it over 0.3 seconds. Now, yeah, let's go ahead and do this. First thing I'm going to do is to insert my first part, which is that hinge. So insert my 3D part. I'm going to call it the hinge. Okay, right click properties, hinge, and hinge. I'll make it orange. Basically, it's just a small cylinder. So double click on 3D shape so that you go into part design. So on that vertical plane, I will sketch a tiny little circle. Oh, try it again. Why don't I make this dimension maybe a radius of 1 centimeter? If things don't look good, we're going to come back and fix it. And then pad this thing. Sure, let's make this thing 5 centimeter. Okay. Now this is going to be our hinge. Then we're going to insert our plate, insert, or the bar if you want. Insert a 3D part. I'm going to call this thing rod, bar, bar, and then I'll make it yellow. Okay, so let's go to the bar and make it. We're in part design, yeah, we're in part design. So on that vertical plane, I will sketch that rectangle, and I'm going to make my job a little bit easier. I'm going to make this thing a centered rectangle, right at the center being there, and I'll dimension these things in a minute. So that length is 1 meter, 1 meter, and that width is 10 centimeter. Okay, and because I want a hole here, why don't I also project that circle, or draw a circle? It's up to you. Project this just the edge. Okay. All right, right there. Exit and pad it by 1 centimeter, right? 1 centimeter. Okay, so basically there is my structure. Yep. Now, before we go out, let's go to assembly design and fix that hinge. So we're going to fix that hinge. Okay. And then I'm going to make a revolute join, trying to make a revolute join between these two. So let's go and do that. Revolute. It doesn't matter which template you use. You're going to get, I think, 10 of them. I use the third one, fourth one, I'm not sure to do that. Yeah. So I'll use, really doesn't matter. Okay, how about, yeah, I like that one. Axis, plane. So this axis and the axis of the bar, this plane and that plane, and I don't need this last option, so just delete it. That's going to be revolute. So say OK. You don't have to do contact calculation. All right, that's pretty much it. Now, next thing we're going to do is to go to motion design. By the way, look, there's a revolute. Oh, I forgot to fix this. I thought I did, but fix the hinge right there. Second condition. Good. Now we're going to go to motion design. I just want to remind you that these problems can be done with mechanical systems design and mechanical systems experience. But recently I've been using these motion design, which is the glorified version of those two that I mentioned. Immediately it's going to create joints. There's going to be a revolute joint, and because these things that I created were in the assembly design, and now they're going to be transferred. So, okay, they're going to be transferred to, you can see that, to the joints, revolute and fixed. Now, if you go to bodies, this hinge, if you notice that there's a hinge and there's a bar. If you double click on the bar, it shows you that the properties, default properties of steel has been used. If you don't specify material, it's going to be default properties of steel with a mass of 7.7 or 7.7, and that's exactly my calculation shows right there. And for the the hinge, it really doesn't matter. Again, steel is used, but since it's not moving, it doesn't matter because it's a stationary fix. It really doesn't matter. Okay, good, good. What else do we have here to show you? Yep, gravity has been applied in this particular problem. Gravity does not play a role because the velocity immediately before impact and immediately, uh, obviously, angular velocity before impact is zero. After impact, it's going to something that we're going to calculate, and G doesn't come into the picture because the spring is not an impulse, does not have an impulsive load. Gravity does not have an impulsive load either. Okay, so let's go ahead and do this. Now, spring, as far as the spring goes, go to mechanism, scroll down, you find the uh, just 1 second. Uh, I'm sorry, go to machine elements. Here's the spring. There's a spring. So you have to go to the mechanism. You have to go to machine elements, spring, and there is a torsional spring. Now to get to basically get the location of it, we're going to do two things. We're going to select that circle, the orange, and the back of this, and it's going to put it immediately right there between those two, okay? So I'm going to select this, all right? And for the second one, I'm going to use that. And notice that it just places it there. And for the number, it says the spring is uncoiled at the vertical position. And even if I didn't say that in the, even if I didn't say that here, I really should have. This is uncoiled when the spring is in the vertical direction. So that's going to make this thing 0. And the value of the stiffness is, I believe, we wanted to take it to be 400 Newton per meter, okay? Newton meter per, what did I say? Just 1 second. Yeah, Newton meter per radian. Yeah, that's what it is, 500. Okay, no damping. It's good. All right, now let me turn this thing around so you can see it. Okay, so what we want to do is we want to specify the force, but to do that, I need to define a function first. So I'm going to go to mechanism, function, and there we are. Let's go up here, and I want a force, okay, and we want to specify a I want to specify a variation of it. See that? You pull this thing down. You don't want a constant. You pull it down. You go to data points. Okay. So let's see now. At zero, the force is 1,000. course, is 1,000. All right. Add another row at 0.01. Also, the function is 1,000. Okay. And then add another row. A tiny amount after that. Maybe 0.01. It drops to 0. And let's say we go all the way to, all the way to 0.3. The simulation duration, that is 0. And I want not cubic, I want linear right there. So you can see that I have to change this thing. You see, I don't want a natural cubic, I want a linear. So the first 0.01 second, it's, just want to make sure, let me clean this up. This is okay. Yeah. So if you look at this, the area under it is going to be 1,000 times that distance, which is 0.01. So it's going to be 10 impulse of 10. Say okay. Now we're going to go to force, applied force. Careful here. Where do you want to apply to that edge? In what direction? Direction Y. And how do I want to do that? I want to use a function, right? Magnitude by function. I already created the function, which was somewhere here. Let's go find it. There. There. See? Yeah. Let me just make sure that the direction of it is okay. In the direction Y, I put down 1,000. Okay, good. All right, that's anything else? So I think for now that's okay. But it's, yeah, for now it's okay. So let's go ahead and check it out. We go to simulation. Oh, what's the duration of the simulation? If you double click on this dynamic step, it tells you duration of 5. I don't want a duration of 5. I'll say 0.3, okay? And yeah, okay, let's go ahead and check it out. This will actually give you the preview. It's not going to run, it's going to give you preview. Let's check it out for a second. Click on that. Get a preview. If that doesn't look good, it means we have to go on. Basically, yeah, that looks good, right? That's the way it should be. All right, so I'm going to exit this. Now I'm going to run it. There's the run. Wait until this thing finishes. Okay, it did finish. So we go here and we select our result, dynamic response. Let's go to result, play animation. And let's, there. So if I play this thing continuously, and I can slow it down here, of course. Okay, so it looks good. Now we're going to go, okay, to get the 2D plot, we're going to go to 2D plot, and we're going to go to the body, which is the bar, and angular velocity about the x-axis, not the y-axis, x-axis. There, you can see that This is where the load was applied. Let me show you also the, can I show the force? Yeah, you can see that in the y direction. Okay, you can see that the load dropped at 0.01 seconds, so to 0. So if I say, show me that, this is where the impulse finished, okay? And look at the value, 7.55 rad per second. 7.55 rad per second, close enough. Now, if I want to see the maximum deflection, this is where the impulse stops, all right? If you want the maximum deflection, you go to the torsional spring and look at the deflection and add plot, and look here, the maximum is, what's the number that you see? In magnitude, it's going to be 15 point something. Let me not plot this, just look at the value here, 15.79, something like that, and there, close enough. Okay, so that takes care of this problem. Now, notice that I did not even have to go all the way to that 0.3 second. I could have gone to maybe looks like maybe point, I don't know, 0.1. It'll pick up that first beat. If I run it, okay, and go to results, plot results, and if you, where's this? Well, actually, it's done here. Sorry, I didn't have to plot it. It's right there. So this is the 15. See that, the 15? 15. And if I add, for example, uh, the velocity, I get this, which is 7 point something. All right. All right, Fitz. Good luck.